In this lecture, we are going to learn about different types of fluids. So fluids can be classified on different bases, and in this lecture we will see how we are going to classify fluids on different bases. So the first basis, it is based on Newton's law of viscosity that we have studied in the last lecture. So based on whether the equation is following Newton's law of viscosity or it is not following, we can define the fluids as Newtonian and non-Newtonian fluids. So this equation we have derived in the last lecture. So this is known as what? It is a Newton's law of viscosity, and it states that shear stress is proportional to rate of shear stress. And this mu, it's a constant which is known as dynamic viscosity or simply viscosity. And from this equation, it is clear that the relationship between shear stress and rate of shear strain, it is linear. Now if we plot this equation on the graph, in which on x-axis we are having rate of shear strain du by dy, on y-axis we have shear stress tau, and if we are plotting this onto this graph, what we will get is a straight line. So it clearly indicates that as the relationship between shear stress and rate of shear strain, it is linear, we will get a straight line on the graph. Now the fluids which follows this, so for the fluids for which the relationship between shear stress and rate of shear strain is linear, they are known as Newtonian fluids. Now if we rearrange this equation in such a way that this du by dy I am shifting to LHS, mu will be equal to tau upon du by dy, and it is clear that tau upon du by dy is nothing but what? It's the slope of this curve. So dy by dx is the slope. So likewise on y-axis we have tau, on x-axis we have du by dy. So tau upon du by dy is nothing but slope of the line that we have here. So from this it is clear that for Newtonian fluids, mu will be a constant. So mu will be constant throughout. Whatever the rate of shear strain you have, the mu is behaving, the mu will be same, and the fluid is going to behave in the same manner. But there are some of the fluids which are not behaving in the same manner. It means that the dependence between shear stress and rate of shear strain, it is not linear dependence we have. So it is a non-linear dependence present. And such a type of fluids are known as non-Newtonian fluids. So instead of this equation, they may follow some another equation. Now what is that equation? So this is one equation, it is shown here. So tau equals to m into du by dy raised to n. This is known as power law model. And here the small m stands for flow consistency index, and the small n it stands for flow behavior index. And here it is clear that shear stress and rate of shear strain, they are not in a linear relation. They are having non-linear dependence. And now this is known as power law model. And now we can say the fluids which does not obey the Newton's law of viscosity and which is having some non-linear dependence between shear stress and rate of shear strain, such a type of fluids are known as non-Newtonian fluids. Now if we plot this equation on the graph, what we will get is, so on x-axis we consider rate of shear strain du by dy, on y-axis we are considering shear stress tau, and after plotting this equation on the graph, we will get different types of curves. So if we are considering n equals to 1, we will get a different curve. For n less than 1, n greater than 1, you will have a different curve onto this graph. So first we will consider n equals to 1. So if n is equal to 1, it is clear that shear stress and du by dy, they will have a linear relationship. And if it is plotted on the graph, what we will get is a straight line. So it is same as we have seen here. So for Newtonian fluids, n is equal to 1. So when we are talking with respect to power law model, we can say that in power law model, if n is equal to 1, the fluid is treated as Newtonian fluid. Now here, what we can do is, we can draw slopes at different locations. So here one slope I am drawing, at some other location a slope is being drawn. Now it is clear from this that the slope is remaining same everywhere. It means that slope is nothing but mu, and mu is remaining constant throughout the slope. So whatever the rate of shear strain you can have, the viscosity will be a constant. Now if we consider n less than 1, and if you plot for n less than 1 the equation on the graph, you will get a non-linear relationship between tau and du by dy. Now this non-linear relationship, it is for what? N less than 1. Now it is clear from this curve that as rate of shear strain is increasing, the slope is continuously going on decreasing. It means that the slope mu, so mu is continuously decreasing. So with increase in rate of shear strain, the viscosity will decrease for this type of fluid, and this type of fluid, it is known as pseudoplastic fluids. Now here again, if we plot the slope triangles at different locations, so here you can plot one slope. At some another location, the slope can be plotted. Here it is clear that the slope is decreasing. It means that mu go on decreasing when the rate of shear strain is increased. Now for the third case, that is n greater than 1, if we are plotting it, we will get some such a kind of curve, and this type of fluids are known as dilatant fluids, and for these fluids we have n greater than 1. And again we can observe here the slope, here it is smaller and here we have a larger slope. So it means that the slope is going on increasing at rate of shear strain increases. So it means that mu increases with increase in rate of shear strain, and such a type of fluids are known as dilatant fluid, DILATENT. And in addition to these fluids, we have one fluid which is known as Bingham plastic, but it is showing some different behavior. What different behavior this type of fluid shows? So it is clear from this curve that here we can observe some initial shear stress to be provided. These three fluids, if you consider, what is happening? Even a small shear stress, it is being provided, the fluid is moving. So with a small shear force also, the fluid will start its deformation. But in this case, you have to give certain initial shear stress. This amount of shear stress have to be provided initially, and afterwards what will happen? The fluid will start its motion, and such type of fluids are known as Bingham plastic. Here n is equal to 1 because it is showing a linear relationship, and in addition to this term, this amount of shear stress will be present here. Now what is the example of Bingham plastic? If toothpaste we can consider, so if a toothpaste we can take, so if you just keep it in an inverted position, the paste will not come out, but when you press the tube, what will happen? The paste will come out. So it is nothing but what? You are pressing it, means what? You are providing some initial shear stress. So after the application of some shear stress only, the paste is moving out, and such type of fluids are known as Bingham plastic fluids. And this fluid, it is not showing the behavior of fluid, that's why it should not be considered under the domain of fluids. Now the next classification is ideal and real fluids. So it is on the basis of viscosity, whether the viscosity is there for a fluid or it is not. So first is ideal fluid we'll consider. So ideal fluids are those for which the viscosity is equal to 0. It means that these fluids are non-viscous in nature. Means there will not be any internal friction present. That's why it is written that these are frictionless. So ideal fluids are those for which the viscosity will be equal to 0. See, in practice, will not have any fluid which is having 0 viscosity. But here it is an idealization that we are considering, that viscosity is equal to 0 for some of the fluids. Now, exactly where it is going to happen, we will see later on. But just now keep in mind that ideal fluids are those which are not having viscosity. So viscosity is equal to 0. And as the friction is not there, so between the two layers, between two adjacent layers, there will not be any friction present. So no friction present, it means that there is no development of shear stress. So shear stress will be equal to 0 in this case. Now we can consider example for ideal fluid. What exactly ideal fluid we can demonstrate here. So let us consider one plate we have, and some fluid is flowing with free stream velocity. Now as this fluid is flowing and it is coming in contact with this solid boundary, what should happen? Because of no slip condition, the first fluid layer will have 0 velocity, as this plate is stationary we are considering, and in the y direction what will happen? The velocity will continually go on increasing, that we have seen before. But in ideal fluids, what is happening? Mu is equal to 0. One layer, it will not resist the motion of another. So what will happen here? The first layer will have 0 velocity, But whatever the rest of the layers you have, they will move with the same velocity with which they are coming in, and hence the velocity profile you will get will be like this. So such a type of fluids are known as ideal fluids. Now coming towards real fluids, what real fluids are? So definitely real fluids are those which are having some viscosity. So viscosity is not equal to 0, and because of which they are viscous in nature and some friction between the two layers will be present. And as friction is present, there will be a development of shear stress, and shear stresses are again non-zero quantity. To demonstrate what real fluid is, so let us consider same kind of plate which is stationary and over which some fluid is moving with some free stream velocity. And when the fluid will come in contact with the solid boundary, what will happen? The first fluid layer will come to rest, and the rest of the layers they will continually have increase in its velocity. So same this kind of fluid layer, fluid velocity profile you will get. So this is behavior it is shown in case of real fluids, and this is a clear distinction between ideal and real fluids. And ideal fluids are having zero viscosity, whereas real fluids are having non-zero viscosity. There are no shear stresses developed in ideal fluid, whereas in real fluid shear stresses will be developed. And velocity profile in case of ideal fluids it is rectangular, whereas velocity profile in real fluids it is parabolic in nature. Now we'll understand why we are studying this ideal fluids. So definitely this is not physically possible. It is an impractical situation we are considering. But when we talk about such a situation, that is a plate, stationary plate over which some fluid is flowing, and what is happening? The first layer will have zero velocity and you will have some velocity variation. And we have seen that after some distance in the y direction, what is happening? The velocity is coming closely to the free stream velocity, and later on the variation will not be there. So a straight line you will get here. So this behavior, this velocity profile after this boundary layer, it is somewhat similar to this rectangular velocity profile, and hence we can say that now the fluid viscosity it is not significant in this region. It is only significant in this shaded portion in which the velocity is varying continuously. So we can say that ideal fluid approximation can be done out of this boundary layer, whereas within the boundary layer the viscous effects are significant. So this is the reason why we are talking about ideal fluids. And the third kind of classification, it is based on the compressibility of fluids, and it is known as compressible and incompressible fluids. Now, what is the meaning of compressible fluids? So, compressible fluids are those of which the density is not remaining constant. Means the density varies. If you consider a fluid whose density is not remaining constant with the application of pressure or with the application of force, we call such a fluid as compressible. Now, we can demonstrate this. So let us consider a container we have and within which we have gas. So this is a piston on which you are going to apply the force. Now here you can observe from its molecular structure that the gaps between the two molecules they are very large. Now what will happen? When you are applying force on it, after the application of force, there is a chance that the molecules can come close together. And because of which, what is happening? The mass whatever contained here in this volume, now the same mass it is being contained in the small volume, because of which the mass upon volume this term will increase. Volume is taking less volume it is taking for the same mass, we can say that the density is changing in this case, and such type of fluids are known as compressible fluids, and this behavior will be shown in case of gases. And it is because of what? Molecules are widely spaced and they are compressible because they can now have a chance of coming close to it. Next type of fluids are incompressible, and definitely incompressible fluids are those for which density is going to remain same. Now let us consider same condition, same container we have. Now here liquid molecules we are having. Now these liquid molecules on molecular basis, on molecular level, they are very close to each other. There is no chance that they are again come close to each other. So when you are applying the force, there is no gap present. So there will not be any movement you will have. And hence even after application of force, the volume will remain same. So volume is not changing. So mass upon volume here and here it is same. That's why we can say density is equal to constant. So compressible are those for which density is changing, and incompressible density will remain